Tactical espionage action. How do Death Stranding bridge babies work? Death Stranding comes out today, and if you're not familiar with the game, it involves weird fetuses that you carry on your chest so you can see ghosts. But how could you do something like this? It's the main mechanic of the game. I have played a number of hours of Death Stranding. If you want to know my review, we can get to that a little bit later. But how could something like this be possible? How could we replicate the miracle of life in an artificial form like this? Well, actually, there's a lot of science to a bridge baby like this. And what we would be dealing with then is some kind of artificial womb. So what would you need to replicate the miracle of life such as this? Well, you need a number of things. The first of which being you need some kind of housing to act like the womb to protect the fetus as it develops or just as it matures. And in the game, this is accomplished with the pod. Now you see the umbilical cord here, and when we do research with artificial wombs, we actually sometimes use the original umbilical cord because it's something that's hard to replicate. So this could be kept open with medical means if, say, this was taken out of a mother or what have you. The next thing that you would want in a pod like this, if it was attached to Norman Reedus, not, a guy from Walking Dead, Norman Reedus, but like walking over rocks for 40 hours, Norman Reedus, you would want some kind of attachment that would provide an amniotic fluid to the bridge baby. And to the game's credit, every so often you do have to flush out and recalibrate the baby's fluids such that it is happier. And this is where you are inserting nutrients and the solutions needed to keep the baby happy. You would also want some kind of dialysis system. This is going directly into the baby's bloodstream, like it does in a normal pregnancy, directly into the baby's bloodstream with some kind of machine where deoxygenated blood can come out of the fetus, be oxygenated, and then return into the fetus. So you want some gas line in that can provide oxygen, air, nitrogen, the normal composition of atmospheric air on Earth or wherever they are in Death Stranding. And then you would want some gas outline where you could remove waste from the blood, it's functioning as a kidney. And you can remove carbon dioxide from the blood. And you'd also, like I said, you could insert any medications or extra fluid into this dialysis system. Nutrients is a different thing. It's harder. It's something we haven't really cracked yet. But lastly, you would want some kind of temperature apparatus to keep this artificial womb at a real human body temperature, around 35, 39 degrees Celsius. So if a bridge baby in Death Stranding had all these attachments and it was constantly supplied with fluids and air and nutrients and it was attached to Norman Reedus's blood, maybe as an artificial dialysis kind of system, there might be some kind of universe in which also, with the addition of heat, this baby could mature and survive in the Death Stranding. But we've actually done something like this in real life. Even though the first artificial womb was patented in 1955, it took all the way until about 2017, you may have heard about this story, where we took premature lamb fetuses and we took them out of their wombs and we put them into artificial wombs where were basically just plastic bags, and we had all of this set up and they were able to survive and mature and develop in the artificial womb for a month. Now, the ethics of doing this with real human babies and how technical it would have to be, and should we do it, for what kind of baby should we do it, for how long, that's a whole nother question. But researchers, the ones looking into those lamb fetuses, think that maybe this kind of technology, a bridge baby-like apparatus, could be 3 to 5 to 10 years out and could help premature babies that need additional growth. It's easier than having them in the ICU or something like that. So this is everything you would need to make a real bridge baby. Could all that be attached to just Norman Reedus? I don't know. He's carrying hundreds of pounds as it is of nonsense. Why not? Hello and welcome to, you might get how I think of the game. Hello and welcome to another edition of Because Science Live, the live show on this channel where I take all of your comments, questions, and corrections and I try to address them off the top of my head. Yes, it's live. Look, I'm not a working scientist. I don't have a PhD. I'm just a super nerd who knows a little bit about a lot of sciencey and pop culture-y things. So if you have a question for me that you think I might be able to answer or at least make entertaining, put it in the chat on YouTube or wherever you're watching this and I will have Voice of the Void Nate get to it. If you are spamming the chat, we will never ever answer it. Make sure it's nerdy, get in there, get quick. What's cracking, Nate?
Hey, how's it going today, Kyle?
You don't sound like Nate.
I've got a little cold today.
That's what it must be. What we got first?
First off, Serapio Martinez asks, how's the weather in the void? Starting it off with a softball.
It's weird. It's like an odd... It's more like a presence than a temperature.
Okay.
If that makes sense.
That definitely answers it once and for all. Okay, Robert Messiah asks, is gelatin a solid or a liquid? My daughter would like to know.
Huh. Is Jell-O a solid? Is Jell-O an amorphous solid? What defines a liquid? So, something like a Jell-O. So let's say you have a gelatin that you and your daughter are wondering about. Let's say you have a gelatin. Now, what would the easiest way to classify this? What would be the easiest way to classify this as a fluid? Well, normally, which you might learn about in school when you get a little bit older, is that normally things that are in the fluid state will fill the volumes that they occupy as much of the volume as they have, which is to say that if you pour water into a glass of water, if you pour some amount of water into a glass of water, let's say we drip some into here, we put some amount of water into there, it will fill as much volume, it will spread out and fill the volume as much as it can. Now imagine putting some Jell-O into a bowl or a flask like this. What will the Jell-O do? Will it spread out to fill the volume? Air does this too. If you breathe into a box, your breath will fill every corner, every nook and cranny of that box eventually, as will water if there's enough water. But a solid will maintain its shape and it will not fill the volume in which you put it. So I would consider gelatin solid. Circular reasoning. But I would consider gelatin and Jell-O to be a solid because if you put it in something like a container, it will not form itself to the shape of that container unless it is to the temperature, maybe, bridge baby temperature, that it will become more of a liquid. It will melt, so to speak, and then it will fill the volume, and then it would be more liquidy. But I'd say gelatin is a solid. That's a good question. I like how you're so curious. What's next?
All right, Java Monk asks, in a Cyanide and Happiness cartoon, a guy karate chops in half the following things: a house, the planet Earth, and the Milky Way galaxy. How much force would these feats take?
What would chopping apart a galaxy even mean? A galaxy is not a solid. It's bound together gravitationally, so with a giant, with all the mass in the Milky Way galaxy, it has a center of mass around which everything is spinning. And so one way to, So if you wanted to karate chop a galaxy, theoretically, what you would do, well, this is stupid, but what you could do, since everything, let's say you have on average most of the mass located in some amount of space. Light years and, cubic light years and all this material. So you have all this material spinning around this center of mass on average. And so what you would want to do, that's the wrong direction. And so what you would want to do is eliminate the center of mass, or as much mass from the point, or in the rotational point that you could. So if you were to somehow super villainy or super science fiction-y, if you were able to just pop this mass, a great amount of mass from the center out of existence, then the material around the edge would no longer be as gravitationally bound, and it should fling, or more so, fling itself out into the reaches of space. And this is kind of like if you were imagining spinning a rock on a string and cutting the string. It's a gravitational string in this case. And so this would be like eliminating the sun from our solar system. If you suddenly blinked it out of existence, the planets would spiral off. Well, they would actually travel in straight lines that's tangent to the circle that they're on, but they would fling out into the surrounding interstellar medium. So if you want to karate chop a galaxy, remove the center of mass with something. Are you Happiness or just Cyanide? What's next? Don't laugh at that.
Okay, I'm
Thank
done.
you.
I'm done
Thank
laughing.
Thank you.
Zachary Sieg asks, I just want to know how many markers you've gone through in this show.
I do. Okay, so I would say average pack comes with 5. We've done, let's say 2 weeks, it's closer to 3. So let's say 3 weeks on average for a pack of markers, maybe even 4. Okay, so 3 or 4 weeks on average for a pack of 5. And the episode coming out, I believe next week is either the episode we filmed this morning is episode 271. So the episode that came out, that will be coming out, is 270, which means if you divide that 270 weeks by 3, let's round 3.5 up to 4 and 270 up to 300 just to come close. You get about 100 times we've switched it with 500 markers.
That's a lot of markers.
Or so. In 5 years, I think that's okay. 100 markers a year is what we go through.
Foodie and Phil asks, other than cows, what other animals contribute to climate change?
Well, off the top of my head, I know cows are one of the easiest culprits to think of off the top of your head, but it's more grazing livestock. So it's not just cattle. This would be, pigs and sheep and things we raise. Think of it this way, ungulates that eat a lot of grass and stuff that needs to be heavily digested, therefore they produce a lot of gas, and we cultivate these animals in mass. So all animals, I don't know if this is true actually, but I would guess that nearly all animals that digest in a similar way produce methane and then fart. But cows are such a big contributor because A, methane is a very strong greenhouse gas, but B, there are so many cows. There's millions and millions of cows in the United States. So it's because there are so many of these animals all producing a very strong greenhouse gas. So any other livestock animal that we have millions and millions of is also going to be a significant contributor. Although I don't know the exact numbers off the top of my head. I would guess that pigs from pork and bacon production and ham production would be up there, but I don't know. What's next?
Dylan asks, kind of piggybacking off this one a little bit, why do some smells travel through the air faster than others? Example, a fart versus perfume.
I don't know. You ever walk through a Macy's?
Lots of farts there.
No, I mean because the perfume section, and you can. I knew you sounded different. So what smell is literally particulates moving through the air, being, volatiles, either being, mechanically sloughed off of some material or they're evaporating with moisture or what have you. But it's particulate going through the air and into your nose and being detected by your brain as something that is smelly. Now, there are going to be different concentrations of this depending on what is producing the smell. So concentration is going to matter, and what the chemical itself is going to matter in terms of its potency, and your brain is going to matter in terms of how much you pay attention to a smell. For example, air, if you were an alien, probably has a certain kind of smell, but our brains most likely tune this out, like it's tuning your nose out right now, even though now you see it, now that I said it. But it's tuning certain smells out, so we pay attention to certain smells because they have some kind of valence to them, so they signify importance. So if you suddenly smell a methane kind of smell, you almost smell it instantly because you think natural gas, you think explosion. So we're more attuned to certain smells than others. We're probably more attuned to fart smells because we consider them either repulsive or disgusting, or they indicate some kind of rotting food evolutionarily or something like that. And so we'd be much more attuned to that smell than, say, a pleasant smell, right? If you're just going through your day-to-day life and you pass like a rose bush, it might not be like, where are those roses coming from? But if you walk past a rose bush and you smelled a fart, now that would be weird. I'd start running. Wait, what? Never mind.
Jake Habes asks, hey Kyle, I'm currently a bio major in my junior year, and I've come across...
Nice. Good luck on your studies.
And that ties into the question. And I've come across a difficult class with a horrible professor. How do you recommend studying for such a class with no help from the professor?
Well, I'm sorry that you're in your that's the situation you find yourself in. I agree with you. I also had a bad experience in college where I had a professor that I did not view as helping the class very much, and because of that, it was my only bad grade I've ever gotten in a college course. And I blame the professor. But, you know, it's give and take. The professor is a huge part of it, and the professor can make whoever he or she is or they can make a huge difference in terms of your interest level, how they present the material, the excitement with which they present the material, their office hours, how much they engage with students, do they remember your name, how quickly do they go through notes, do they let you study, blah, 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 blah. So that can make a huge difference, and I'm sorry that you're having a bad time. So I guess if there's really no way to make it more known to this professor that you really need help, I would become your own professor in that, not to say this is going to remedy the situation necessarily, but I would take it upon yourself to recognize which deficiencies you are having, where you are struggling in terms of the coursework, and then rectify those by either focusing on those really specifically and hard by yourself, or even I bet there's someone else in your class who has a similar problem with the professor that you could reach out to and say, you know what, maybe we can help each other. What aren't you understanding? What are you understanding? Oh, that makes more sense when you say it like that. So I would say reach out to your fellow students, see if anyone's having a similar problem, and if it can't be rectified by going to the professor and really being honest with them, then I would say take it upon yourself, be really honest with what you don't understand, don't be afraid to ask questions, and don't be afraid to reach out to other people. That's what I would say.
Dragon Dude asks.
Because if you have a problem with the coursework or you have a lot of questions about something very specific, very, very high chance that someone else does too. And it wouldn't hurt to put yourself out there a little bit. Dragon Dude.
Dragon Dude asks,
Woo!
Hi Kyle, what would happen if you reduce the distance from the moon to the Earth by half?
Well, you would... Okay, so if the moon got a lot closer to the Earth, this is I hope you know this is a very hard question, and I don't know exactly what would happen off the top of my head. But if you had the moon a lot closer to Earth, and this is not to scale, but if it was a lot closer to Earth, a couple things would happen if I had to guess off the top of my head. A, it would become a lot bigger the night sky. Nights would become a lot brighter. How bright? I don't know. Maybe you could read at night. That'd be fun. Go out to a graveyard and read a scary book. That sounds fun. Sorry, it was just Halloween. It would get closer in the night sky. It would get brighter. The tides would become a lot more, well, it depends. Oh, well, if you say half, I'd have to do the math. But the tides would increase and decrease accordingly quite a bit. I don't know if it would put real gravitational, like tidal gravitational stress on the planet itself. And I don't know if that would be within the Roche limit for the moon. I'm going to guess it's not. That's a very hard question. I'd say search for that because that's very interesting. I do not know off the top of my head exactly what would happen because that seems like a very complicated scenario. So I'm not going to speculate and possibly be wrong forever on the internet.
Trevor Lang asks, Hi Kyle, if you could...
Hey Trevor, frequent commenter, I think.
You could invent a unit of measure, what would you measure and what would it be called?
I'm narcissistic in the way that I'm never gonna, because I'm not a working scientist, I'm not publishing, this is never gonna happen, but I love the idea of having some kind of unit or some kind of force or law or something named after me. I just think that would be a really fun legacy to have. Like even if you do nothing else, you're like, well, that would be exactly 7 hills. You know, I think that would just be fun. So what would my unit of measurement be? Well, I came up with something stupid for an episode that I now call the Hill engine. And the Hill engine is a way to propel spacecraft. And what it does is uses the most brute force method I could possibly think of, which is throwing blue whales out the back of the spacecraft at supersonic velocity. And if you throw a couple of blue whales out the back of a spacecraft at supersonic velocity, you will achieve about the same amount of thrust you can get from a Saturn V rocket, and that's a Hill engine. It is incredibly wasteful. It is incredibly damaging. It will depopulate the planet of blue whales very quickly, but you'll be thrusting.
All right. Aaron Bagel asks, hey Kyle, is there a way for us to store radioactive waste out in space rather than underground?
So the problem with radioactive waste is obviously you want to put it in a place where no future humans are going to get to it. Right now, our idea of doing that is just very brute force, which is find a big mountain or find a very uninhabited area and just dump it down a big old hole and then put a sign that can be read in 1,000 years and say, don't open that. Now, obviously, it's not a perfect solution. As you suggest, why don't we just shoot it into space? Now, I don't know the exact reason. I don't know what the reason that NASA would give or the government would give, but my estimation would be that if you tried to move radioactive waste to space, two things. One, cost. It is very, very costly to get just a kilogram into space. Before the privatization of space, like $10,000 per kilogram. So we're talking about millions and millions of dollars to get radioactive waste into space. We could park it in orbit, but it's going to cost millions and millions and millions of dollars. And I'm going to guess that the cost of shoving a couple barrels down a hole is less than that. The second thing is that space is hard and space can be dangerous, and there have been accidents. Rockets have blown up on launch pads. Rockets have blown up, there's been, destruction in the atmosphere and those kind of things. So you can lose a satellite if something goes wrong with, say, your Hill engine, okay. But if radioactive waste explodes in the atmosphere, say, I don't know, around a city, Cape Canaveral, wherever, radioactive waste exploding in the atmosphere sounds like a supervillain plot, and I'm guessing they don't want to take that chance, or that would be one of the reasons why you wouldn't take that chance of possibly irradiating an entire area and making it uninhabitable for thousands of years. That sounds like a good reason not to try that.
Reggie asks, what's the probability to use rail guns to fire spacecraft into space?
Oh, railguns to fire spacecraft into space. So what you're describing is, let's say we had a planet like this. This is not to scale. You would want to construct some kind of railgun system that instead of using something like a Hill rocket, a Hill engine, and blue whales to get yourself into the atmosphere, you start instead on the ground and you use electromotive force. You put electricity through giant rails, and this induces magnetic fields, and this magnetic field pushes on a rail that sits at the center of these two parallel rails, and that force can get really, really fast. That force can get really, really high, and because it's all electronically calibrated and coordinated, you can give little bursts to this as it goes and goes and goes. So you can accelerate projectiles to incredible velocities. You can get railguns moving many miles per second, something like that. So what would be the advantage? Well, you might be able to save some money, but you'd have to go all the way through the atmosphere with a projectile, which the atmosphere is a lot thicker than space, necessarily. And so it's going to take a lot of energy to launch something fast enough to get it through the atmosphere if there's no additional propulsion. I don't know what the exact problems are because I've never designed one of these things in my head. But one of the biggest ones I can think of is that if you wanted to do this, like basically a giant gunshot, like shooting a spacecraft like out of a cannon into space, one of the biggest problems would be little a here, which stands for acceleration. So if you are accelerating in, say, a Hill engine, you are pulling maybe 3 Gs. This is what astronauts pull typically, and the human body can handle this for a short amount of time. But to get going many miles per second with along the length of a rail system, A here, might be a lot more than 3 Gs, and so either the rails have to be super, super, super long and therefore really costly, or they're going to be short and the acceleration is going to be super high, and then human bodies might not be able to take that kind of acceleration, which means the only way you'd be able to use a railgun system like this would be to shoot cargo and satellites and other things into space, which might be viable, but I don't know. Last question.
Dan Deniza asks, hey Kyle, inside of a moving car, when something is dropped from the ceiling, why does it fall straight down relative to the car and not fly back and hit the back of the car?
Great question. So this is a great typical physics question. So if you were traveling in a car, let's say you were traveling in a car, and we're looking at it like this, and the car's moving this way, and now we have an object, and we drop it. Which way is it going to go? Well, that depends on which frame of reference we are looking at. So if we are sitting inside of the car, what velocity does if we're sitting inside of the car, what velocity do we and this object have? Well, relative to the car, we're not moving at all, right? So if you're sitting in the car and you have the object, both of you aren't moving in relation to the car because you're sitting in the car. And therefore, if you drop the object, it would drop as though you weren't moving at all, and it would move straight down. So when you were observing this as yourself in a car, you drop it straight down because you and the car and the object are all moving at the same speed. That is to say, it's as though you're not moving at all, constant velocity, and so you drop it, it drops it like you aren't moving at all. However, if we change this scenario, so now we're looking at it from an outside perspective, you can see that if you were to drop this and then track the path, it would have a path that no longer looks like straight down because we're looking at it from outside and we see it move forward and drop. Say if you threw it outside of the car, it would have, I don't know if this is exactly correct, but it would have some different kind of pathway, and that's because we're changing our frame of reference. I hope that all makes sense, but this is one of the grand insights. The harder things to understand in physics is what is happening really depends on your point of view, and all things are relative. Relativity, and that gets to all that stuff. I think this is correct. Thank you for joining me for another edition of Because Science Live. Whew! What a week. What did we do this week? We had a vlog. We had a new episode all about how to steal Elon Musk's space car, which I'm very proud of because it's super villainy, but I don't condone it. Next week, we have a new episode, which is very fun, I think. Yes, it is. And it's Star Wars related, hint, hint, in honor of The Mandalorian. We have a new live stream, new vlog. Get your questions in onto the previous episode of Because Science. I still sometimes look at those comments. Have a wonderful rest of your weekend. Wait, tomorrow is Carl Sagan Day. So happy Carl Sagan Day. Tomorrow, if you celebrate it, one of the all-time great science communicators who had to have been a lovely person. Cosmos was one of the shows that got me into science communicating. He had such a way with words and thinking and speaking and writing. He was just a monumental force for this kind of thing. I owe a lot to Carl Sagan. So happy Carl Sagan Day, and I believe Memorial Veterans Day is on Monday. Yes. So if you're a veteran, thank you for your service. Enjoy any time off, and thank you from us to you. And have a wonderful rest of your weekend, everybody. And be nice to each other, because unless you have, a bridge baby strapped to your chest, this is all we got.